Welcome to a journey through the cosmos. Ever wondered about the structure of the universe? You're not alone. For centuries, humans have stared into the night sky, pondering over this vast starry expanse. What's out there? How does it all fit together? These questions have spurred countless theories, each one attempting to decipher the cosmic puzzle. From the ancient geocentric model to the mind-bending holographic principle, we're going to delve into the top 10 theories that have sought to answer these tantalizing questions. So buckle up and let's dive into the cosmic mystery together. Have you ever wondered about the structure of the universe, the cosmic fabric that cradles every star, every galaxy, and every bit of matter and energy? For centuries, the human mind has grappled with this colossal question, sparking a cascade of theories. From the ancient to the avant-garde, these theories strive to unravel the complex tapestry of the cosmos. Some have stood the test of time, while others have crumbled under the weight of new evidence. Join us as we journey through time and space to explore the top 10 theories about the universe's structure. Our journey begins with the geocentric model, the oldest theory about the universe's structure. This ancient Greek creation posits that Earth, our home, sits unmoving at the center of the universe, with celestial bodies wheeling in perfect circles around us. Pioneered by philosophers such as Aristotle and Ptolemy, it was the accepted view for more than 1,000 years. But as science progressed, so did our understanding. With the advent of the telescope, astronomers began to observe that not everything revolved around the Earth. Planets appeared to move in strange, looping paths, and the Sun, not the Earth, seemed to be the common center of motion for all planets. These observations eventually debunked the geocentric model, leading to its replacement with the heliocentric model. Despite its inaccuracies, the geocentric model paved the way for further exploration and understanding of our universe. Moving forward in time, we encounter the heliocentric model, a radical shift from the geocentric model. The heliocentric model was proposed by Nicholas Copernicus, a Renaissance-era mathematician and astronomer. This model boldly posits the Sun, not the Earth, at the center of the universe. Imagine the uproar this caused. Earth, dethroned from the center stage, was now just another planet revolving around the Sun. The heliocentric model was initially met with resistance. However, with time and the backing of astronomical observations, it gained acceptance. It was a revolutionary idea that challenged the preconceived notions about our universe's structure. The acceptance of the heliocentric model was not just about acknowledging the Sun's central place in the universe, it marked the beginning of a shift in thinking, a willingness to question and explore. The heliocentric model marked a significant leap forward in our understanding of the universe's structure. We now enter the era of modern cosmology with the static universe theory. This theory was proposed by none other than Albert Einstein, the man who revolutionized our understanding of physics. The static universe theory is based on the idea that the universe is unchanging, a constant in time and space. It's like a snapshot, frozen in time, with galaxies fixed in their positions, neither moving closer nor further apart. But as captivating as this theory might be, it was eventually debunked. The culprit? The Big Bang Theory, which proposed that the universe is expanding, a concept quite contrary to the static, unchanging universe of Einstein's conception. This marked a significant shift in our understanding of the universe, painting a picture of a dynamic cosmos that is constantly in motion. Yet despite its downfall, the static universe theory should not be dismissed entirely. It served as a stepping stone, a necessary chapter in the story of cosmology. The static universe theory, though ultimately incorrect, was a stepping stone towards our modern understanding of the universe. Next, we delve into the most widely accepted theory about the universe's structure, the Big Bang Theory. This theory, proposed by Georges Lemaitre, a Belgian physicist and priest in the mid-20th century, suggests a fascinating narrative of the universe's birth and evolution. Imagine the universe not as the vast, sprawling cosmos we see today, but as a single, incredibly hot and dense point. This point, often referred to as a singularity, contained all the matter and energy that would eventually form the galaxies, stars, planets, and everything we know and love today. Then, in a moment of cosmic drama around 13.8 billion years ago, this singularity began to expand. As it expanded, the universe cooled, allowing for the formation of subatomic particles, and later, simple atoms. Giant clouds of these primordial elements later coalesce through the force of gravity, igniting the first stars and galaxies. Since this momentous event, the universe has continued to expand, a fact that is key to the Big Bang Theory. Indeed, evidence for the Big Bang Theory is compelling. One of the most significant pieces of evidence is the redshift of distant galaxies. As light from these galaxies reaches us, it appears redder than it should be, a phenomenon known as redshift. This is due to the expansion of the universe, stretching the light as it travels to us and shifting it towards the red end of the spectrum. Additionally, the discovery of the cosmic microwave background radiation, or CMBR, offered further support for the theory. This radiation, a faint echo of the Big Bang, permeates the universe and is a remnant from the hot, dense state of the early universe. The Big Bang Theory provides a comprehensive explanation for the universe's structure, but it's not the final word on the subject. After all, science is a constantly evolving field, and who knows what new theories or discoveries might emerge in the future to deepen our understanding of the cosmos. Let's shift gears now to a theory that challenged the Big Bang, the steady-state theory. Introduced by Hermann Bondi, Thomas Gold, and Fred Hoyle in the mid-20th century, this theory proposed a radical concept. The universe has always existed and will continue to exist forever, without any beginning or end. Moreover, it suggested that the universe looks the same everywhere, irrespective of the direction you gaze into. The steady-state theory also postulated that as galaxies move away from each other, new ones are continuously formed from matter that's spontaneously created. This was a bold conjecture, aiming to explain the observed expansion of the universe while maintaining its steady state. However, the theory eventually fell out of favor, as observational evidence began to stack up against it. The discovery of the cosmic microwave background radiation, in particular, was a nail in the coffin for the steady-state theory. The steady-state theory, though ultimately disproven, spurred further research and discussion about the universe's structure. We now move on to a theory that expanded upon the Big Bang, the inflationary universe theory. This theory was first proposed in the late 20th century by a physicist named Alan Guth. It was during a time when scientists were grappling with some puzzling aspects of the Big Bang theory. Guth's proposal offered an intriguing solution to these issues, suggesting that the universe had undergone a period of extremely rapid expansion in the moments immediately following the Big Bang. The central premise of the inflationary universe theory is quite simple. It suggests that in a fraction of a second after the Big Bang, so tiny that it's almost impossible to comprehend, the universe ballooned out faster than the speed of light. This might sound like it breaks the cosmic speed limit set by Einstein's theory of relativity, but it's the space itself that's stretching, not objects moving through space. This theory isn't just a wild speculation, there's actually quite a bit of evidence supporting it. For instance, the cosmic microwave background radiation, the afterglow of the Big Bang, is incredibly uniform across the universe. This uniformity would be difficult to explain without inflation. Moreover, the distribution of galaxies and the large-scale structure of the universe also support the idea of inflation. So how does the inflationary universe theory refine our understanding of the universe's early moments? Well, it helps to explain why the universe appears flat and why it's so uniform on a large scale. It also provides a mechanism for the creation of the small fluctuations in density that later gave rise to galaxies and large-scale structures. In essence, the inflationary universe theory adds a new chapter to the story of our universe, a chapter where everything we know of, from the smallest particle to the largest galaxy, was once packed into an incredibly small, dense point that then expanded exponentially. The inflationary universe theory has greatly refined our understanding of the universe's early moments. Next up is a theory that takes our understanding of the universe to a whole new level, the multiverse theory. This mind-bending proposal originates from the mid-20th century, when physicist Hugh Everett III suggested that we may live in a multiverse rather than a universe. So, what does this mean? Well, imagine our universe as a bubble floating in an infinite ocean. Now, multiply that bubble by an infinite number. Each of these bubbles represents a different universe with its own set of laws and properties. This is the central premise of the multiverse theory. Everett's idea was a byproduct of his interpretation of quantum mechanics, known as the many worlds interpretation. He suggested that every time a quantum event happens, the universe splits into multiple versions, each one accommodating every possible outcome of that event. Yes, it's as mind-boggling as it sounds. For example, in a parallel universe, there might be another version of you, living a completely different life based on a different set of choices and circumstances. From this perspective, the multiverse theory is not just about space, but time and history as well. However, this theory is not without controversy. Critics argue that the multiverse theory is untestable, making it unscientific. After all, if we can't observe these other universes, how can we prove they exist? Supporters, on the other hand, argue that the multiverse theory could explain some of the biggest mysteries in physics, such as the fine-tuning of the universe's physical constants. If there are an infinite number of universes, it makes sense that at least one of them would have the perfect conditions for life. Despite the ongoing debate, the multiverse theory has undeniably revolutionized how we think about the universe. It has challenged our perceptions of reality, prompting us to consider the possibility that our universe is just a small piece of a much larger and infinitely more complex cosmic puzzle. The multiverse theory, though still unproven, has sparked fascinating discussions about the nature of reality. We're nearing the end of our journey with a theory that could unite all others: the string theory. Picture a universe where everything that exists, from the smallest particle to the grandest celestial bodies, is made up of one-dimensional strings. This is the fascinating world proposed by Leonard Susskind in the late 20th century. At the heart of string theory is the premise that our universe's fundamental building blocks are not zero-dimensional points, as suggested by quantum physics. Instead, they are one-dimensional strings. Imagine a microscopic vibrating string. Each type of vibration corresponds to a different particle, and the properties of these particles, such as their mass and charge, are determined by the string's vibration patterns. This radical idea offers a potential solution to one of the greatest puzzles in physics: the incompatibility between quantum mechanics and general relativity. String theory could serve as a unifying framework, a theory of everything, where all particles and fundamental forces of nature, including gravity, spring from the vibrations of tiny strings. Yet, as alluring as string theory is, it's not without its challenges. The main issue is that it's incredibly difficult to test. These strings, if they exist, are thought to be incredibly tiny, about 100 billion times smaller than a proton. This makes it almost impossible to detect them with our current technology, leaving string theory largely in the realm of the theoretical. Another challenge is the theory's prediction of extra dimensions. While we're accustomed to 3 dimensions of space and 1 of time, string theory suggests there could be up to 10 dimensions. These extra dimensions are thought to be compactified or hidden from our perception, but their existence remains a contentious point among scientists. The string theory, though still in its infancy, holds great promise for our understanding of the universe. It's a bold, daring vision of reality that could revolutionize our understanding of the micro and macrocosmos, uniting them under one beautifully complex symphony of strings. If proven true, it would be a testament to the power of human curiosity and our relentless quest to understand the cosmos. Last but not least, we explore a theory straight out of science fiction: the holographic principle. In the late 20th century, 2 renowned theoretical physicists, Gerard T. Hooft and Leonard Susskind, proposed an idea that seems more at home in a sci-fi novel than in a physics textbook. This is the holographic principle, a radical proposition that challenges our perception of the universe and reality itself. Imagine a holographic image. It appears 3-dimensional, but it's created from information that's stored on a 2-dimensional surface. Now take that concept and apply it to the entire universe. Yes, that's right. The holographic principle suggests that our seemingly 3-dimensional universe is actually a 2-dimensional hologram. Our perception of depth and volume could be an illusion, with the real information about the universe stored on a distant 2-dimensional surface. This idea is as mind-bending as it is revolutionary. It suggests that everything we see, touch, and experience, from the farthest stars to our very thoughts, are mere projections from a cosmic boundary that we can never reach, a boundary that contains the entirety of the universe's information in a 2-dimensional form. What's more, the holographic principle might provide a bridge between quantum mechanics and gravity, 2 pillars of modern physics that have resisted unification. If the universe is a hologram, then gravity might be understood as arising from quantum fluctuations on the cosmic boundary. However, we are still in the early days of understanding the holographic principle. Theoretical physicists around the globe are working tirelessly to probe this idea, to test its predictions, and to unravel its implications. They are exploring new mathematical tools, making bold predictions, and pushing the boundaries of our scientific understanding. While the holographic principle is yet to be proven or disproven, it is a testament to the power of human curiosity and ingenuity. It reminds us that the universe is far stranger and more wonderful than we could ever imagine. The holographic principle, though mind-bending, could revolutionize our understanding of the universe and reality itself. From ancient Greece to modern cosmology, we've journeyed through the top 10 theories about the universe's structure. We've explored everything from the geocentric model to the holographic principle, each theory unveiling a new layer of the cosmic web. We've navigated the vast superclusters and delved into the mysterious voids. Science, in its relentless pursuit, continues to unravel the intricacies of our universe. So the next time you gaze up at the stars, remember, the universe is a vast, complex, and ever-evolving mystery, and we're all a part of it. Before we wrap up this cosmic journey, let's remember that the universe is a work in progress, and so is our understanding of it. If you've learned something new today, or simply enjoyed this voyage through the cosmos, do us a favor and hit that like button. It's a small action on your part, but it means a universe to us. Have a theory or an idea we didn't cover? Or perhaps a question that's been burning a hole in your mind? Don't hesitate to share your thoughts in the comments section below. We'd love to hear your perspective on this vast, mysterious cosmos we all call home. If you haven't done so already, be sure to subscribe and press the bell icon. That way, you won't miss out on our future explorations. We've got a whole universe to uncover together, after all. And finally, if you found this video enlightening or entertaining, why not share it with your friends and family? After all, the mysteries of the universe are even more fascinating when shared. Thanks for joining us on this journey, and as always, keep looking up and never stop questioning.